So our topic today is one of the most important. It is nomenclature. So we're just trying to explain that the first thing that we do when a child is born, the first thing that happens when a child is born is that you have to name that child so that you don't call them Iwe. So that's the thing. You name, the name is very special for a child. For some of you who are so spiritual, you even believe that if a name with a name ilastana involve future ya mwana nga name. Then even as you have children, when you have children, most of the times the children are very inquisitive. They'll be asking you, Nishi, what is this? Because they have to learn the names of the objects. So to a language, names are very important. Names are very important. Names of places, names of countries. So those are the things. So whatever subjects that you have, the first thing to understanding or mastering it is to know the language of that subject. For example, if you start looking at computers, you have to understand the language of computers. What is a byte? What is a bit? And all those things. So each and every thing that you are learning, including cultures, names are key. So the other point is that chemistry also has a language. And in this language of chemistry, key is the ability to name for us to understand these aspects. So hence the topic that we're doing today, which is chemical nomenclature. No one will ask you to say define chemical nomenclature. What we ask you is to name compounds. So chemical nomenclature, the definition is there, that the system of names that chemists use to identify compounds and elements. Chemical nomenclature is the system that chemists use to identify compounds. So when a new substance is formulated, the first thing you do is to name it so that you can distinguish it from other substances. So we name something so that we can see the difference with other substances. So today's topic is nomenclature of inorganic compounds. Nomenclature of inorganic compounds, because there's also organic chemistry, which has a language of its own as well. But at the moment, we're just focusing on nomenclature of inorganic compounds. Though the idea is that for you who are doing biomedical sciences, the language you must be more confident with is the nomenclature of organic substances, because organic chemistry is more key than all the other chemistries. But then you cannot learn just organic chemistry starting from the beginning. That's why we're doing A level. You must also know the inorganic part at first year. Then even at the very end, we'll look at organic chemistry. And as you go in second year and third year, you'll be doing biochemistry. So the biochemistry will even be, at third year, it will even be defined properly as clinical, because that's the biochemistry, the type of biochemistry that you have to be learning. So in the naming of compounds, we must look at how many elements are in a compound. That's why there's this chart. So if an element is alone, then it's just an element. So if a compound has two elements only, which is mostly the case, then that is a binary compound. We spend a lot of time naming these binary compounds, possibly because we want to keep it simple. Then if you have three or more elements, then you have a complex compound, or a polyatomic compound. So those are the scenarios. So the first thing that you know about these names is that you must understand the concept of common names and systematic names. So our focus today is the common name first upper. At the beginning we start with common name. So we say the common name is the names that are not based on chemical composition of compounds. So it's just a name, but when you see that name, it can't guide you on how to write the formula for that compound. So most common names were there before chemistry was systematized, and some of them generally described a property about the substance, while others people don't even know where the name came from. Basanga pachoko yaba, and it would be very expensive ukuconvince abantu otherwise. So one of the things that is common is that mercury is called quicksilver because it's shining and all, because of its shining and all. Then there's also dinitrogen monoxide or dinitrogen oxide, which is used as an anesthetic kuma dentists. When you're exposed to that one, where the laughter is coming from, you don't know. Kula bati abantu balaseka fye bakinishita pale abadekera kajoku taurefwanu kuseka, you are laughing. So it's called laughing gas because of that feature. So those are the things. But then there are these ones also, like water and ammonia. No one even knows where they come from, but they are widely used as names. No one knows where water came from, like Ishina. I'm sure the ni Adam or unique, water, because no one knows to say the water was named by this one. No one has even known that. It has just been found to water, and it's very vital to our chemistry. It's very vital to our lives. So water and ammonia, these are common names, such that they are too common that they have even been systematized. Like when you're writing a systematic name for water, you just say water. You don't go wasting your time trying to name water otherwise. So that's the thing. So these common names have limitations. Meaning, guys, is if it was possible to give each substance a common name, looking at its feature, it would waste a lot of people's times. That's why most of the times we just have systematic names. Common names, we've explained that most of them have been used frequently and people have given them those names. So sometimes we use common names if the systematic name is too technical. If the systematic name is too technical, we prefer to use common name. And then sometimes the systematic name is too long. So, for example, photographers, instead of saying sodium thiosulfate, they say hypo. Then, guys, you know that lime or quicklime is calcium oxide. I'm sure you remember. But then for some names, they are too long. E.g., 9,10 secolester 5,7,10 19 triene 3 beta O. This is too long for something that you are using every day. So this one is just the name for vitamin D3. So vitamin D3 is simply better than using all this name. Imagine you want to go to a chemist, then you have to remember all this long. It can waste your time. So guys, the chemical names or systematic names would define them. Let me explain on the systematic name to say the chemical name or systematic names. The net is tripping a bit. The chemical name or systematic name, they precisely identify the chemical composition of compounds. So the one that we use for inorganic, even for organic. So for inorganic, there is this one which is called the International Union of Pure and Applied Chemists. So it was founded in 1921. So that is called a UPAC name. So they meet to review some names of especially the things that they are discovering now. These are chemists, pure chemists that meet every time. So the chemical or systematic names, especially the UPAC names, will help identify how, like when you're given that name, you can easily give the formula. So you must know that. So there's a table there on top. I'm sure you've seen this table where there's a common name and a chemical name. So you will see that for some, like water, as I explained, water, even the chemical name is water, because there's no need of wasting time. Is the name otherwise, because this water is useful even to people who don't understand the chemistry. It's very useful. So your job, guys, for this is to know these things a bit. Don't go gunning this. Just know a few, like slaked lime, aluminum, baking soda, cane sugar, brimstone, especially brimstone, limestone. Just know those. Hypo, as we explained, caustic soda. Those are things you must know. The others, yes, you must have ideas. You can be skimming through, but don't search a shati, ureimba nukwimba yama chemical names. So those are the scenarios. Clifford, do you want to say something? Clifford, do you want to say something? Okay. Mike na yakatataba Clifford. So now, the first nomenclature that we look at for compounds per se is the nomenclature of binary compounds. So binary compounds might either be binary ionic or molecular compounds. Ionic or non-ionic.
No, sir. No, sir. No, sir.
I'm saying your mic is on. Okay. So binary compounds may either be binary ionic or molecular. So what do we mean by binary? Means two. So you can even tell your partner, we're in a binary relationship. Who's that nigga? You can say that. Or who is that girl? That girl. We're in a remember we're in a binary relationship where you're only the two of you in that relationship. The other people, they will make your relationship complex. They will complicate it. So that's how it is. So the first one, ionic. So we have ionic. Remember ionic? Metals and non-metals. And they involved the transfer of electrons from a metal to a non-metal. And then we also have molecular, which involves the sharing of electrons. So in ionic, there's a statement to say that the metal loses electrons, it becomes a cation, then the non-metal will gain those electrons lost and becomes the anion. And the two will be held together by electrostatic attraction, which is the attraction, electrical attraction between a negative and a positive. So metals lose electrons. We're trying to explain that. We're trying to say that ions are formed by removing or adding electrons to a neutral atom. So an atom that has both the number of protons and electrons equal is called a neutral atom. It has zero charge. But then when a metal loses electrons, it becomes the atom when the atom loses electrons, it becomes a cation. So positive ions are called cations. So the neutral atom will lose electrons to form the cation. Then it can be like potassium may lose one, then the others are like that. So potassium, when it loses one, it becomes just K plus. We don't put the one there. Then magnesium loses. So this is how we write the loss of electrons. When something loses electrons, the electrons should be on the product side because they are no longer like there. So you see them on the product side. This is a half reaction because definitely for magnesium to lose electrons, it's losing to something. But then this is how we show how the ion was formed. So these are the things. So these are the common cations that are there. You just have to master them. There is a periodic table at the very end there. This one, it's showing us the charges of the ions from the periodic table. These ones are fixed, these ones, and only aluminum is fixed here. These other there, and then there is silver, which is fixed, cadmium, which is fixed, and zinc, which is fixed. These others are variable valencies. So if you remember, the charge, we also call it the oxidation state. So if there are two or more charges, then you say variable oxidation state. Then the anion is the opposite. It has to gain electrons. So if something gains the electrons, then it has to become an ion. What gains electrons? Non-metallic atoms. Then for them, the key reason why there is this table is for you, because in nomenclature, if the cation, like the metal loses an electron and becomes a cation, when naming the ion, you simply just call it the same name it had before, e.g. potassium ion, magnesium ion, aluminum ion. Like there is no changing of anything. But then when a non-metal gains electrons, it will become negative. Then now there are changes there. You don't just name it to say fluorine ion. You change, you remove the Ne and replace it with De. So always the anions always end with IDE. The anions, the metallic anions, or the non-metallic anions always end with IDE. So as you have seen, fluorine, when it becomes the ion of fluorine is called fluoride. Bromine, the ion is called, which is the anion, is called bromide. You have chloride, iodide, oxide, nitride. Yaba sana common na sulfide. So always remember that, so this is just an emphasis, that always these end with IDE. So the table is like that. So we've explained. So for the non-metallic ion, guys, they have to gain electrons. These ones, the non-metal gains electrons. When it gains electrons, the electrons are on the reactant side. The electrons are on the reactant side. Always means gain. You're adding the electrons to that. So this is a non-metal, gains electrons and becomes the oxide ion. Okay, this is oxygen. Oxygen gains 2 electrons because it needs 2 electrons for it to have a stable configuration of P6. So these are the others. In your own time, you can be looking at them. Sulfide, phosphide. Guys, in this time emphasize, I'm just trying to waste your time. Believe you me, someone, I'm on a nitride, like these examples here, when you are naming them. Uksarandash nitrate. Someone says sulfide, that sulfate. Someone says phosphide. Eno kokwina alandati phosphate. Mwayumvate? Oxide that oxen. What land up. So those are the things that are there. So the rules for naming these things are very easy because you just simply get the name and you get the modified ending. So you name the cation because the cation, the name is just the same. If it's potassium, it just be potassium. Then for the anion, you have to write the modified ending that ends with IDE. It must always end with IDE. This is only the case of binary compounds where you only have a metallic atom, metallic element, and non-metallic element. We're not talking polyatomic yet. I'll put up the polyatomic ions table the next time we have chemistry on Wednesday. So the examples are these. So meaning the names for these, like the formula it's even better because you don't have to start wasting time counting to say yali moyanga. All you do is name the cation and then name the anion with a modified ending. So calcium and bromine is calcium bromide. So remember that this is for these ones which have the fixed oxidation state where the charge is fixed. It's for calcium it's just +2. For potassium is just +1. For lithium is just +1. Magnesium is +2. So magnesium nitride. Lithium oxide. So these are the other names: barium sulfide, lithium iodide, magnesium bromide, and all. So the key for you, so to name Ganabakpera formula is very easy. But to get a formula when all you've been given is a name is a bit tricky. But it shouldn't be tricky for you guys who got credits or better at grade 12. Because what you do there is that someone tells you calcium chloride. So you have Ca2 plus and Cl minus. The only thing that is there, in fact, the charge should be 0 for both. So calcium, it means only one calcium is necessary because it has lost 2 electrons. But then chlorine only gains 1 electron. So for you to be so sure that there are 2 electrons that are gained by the chlorine, it means you need 2 chlorines there. So that's why there's a 2 there. So the formula, you need 2 chlorines because it only gains 1 electron and yet calcium loses 2. So you need an extra chlorine. So that's the reason why there's that. The best also is just to swap the charges, like the number there. This is a 2, you take it below the chlorine. And then the charge on the chlorine is 1 minus, you take the 1 and take it on calcium. And remember that the 1, we don't write it as a subscript. So what you say there is that the formula is CaCl2. Then for these ones, like magnesium and oxygen, this magnesium is losing 2, oxygen by the 2 minus is also gaining 2. So these ones, they are equal, in equal proportionality. You can even, if you want, you can take the 2 there, the 2 there. These ones, you always write them in the lowest terms. So what you end up with is MgO. Why MgO? Because magnesium loses 2 and oxygen gains 2. So you only need 1 atom of each at a point. So those are the things. Barium and phosphorus, kuyachinja again, like that. Remember, you should write them in the lowest terms. So when you end up with something like Ba2, P4, or B whatever, you must know. If you have Ba4, P2, you must divide the 2 there. But then here it's very straightforward. You have 2 plus, 3 minus. The 3 goes there. The 2 goes there. So it will be Ba2, P4. So those are the things. Always remember. So if you're even when you're writing like said sodium oxide, you write Na2O. Why? Because the charge on the oxygen is 2 minus. Then on the sodium it's plus. So those are the scenarios that are there. So you must improve this skill, guys. I'm very impressed with the names. I think the only mistake that Edward made was okulaba at sodium, which was D. It should be Na plus, N formula nitrogen. But all the answers that he put there were accurate. Then here common anion, I'll put common anions, like polyanions, I'll put them in the next lesson because the carbonate has featured here. Carbonate tatabanani ba Edward tatubikapo ka oxygen akano noyiniko bot mulembere. CO, the O must be caps for oxygen. This is cobalt the metal. So always remember not to make these silly mistakes. Instead of putting a capital letter, you will be capital small. Nishnat cross itatumfa no ruse yo. Tatukwata ruse. So these are the things. Now about carbonate, wala baka 3 akali carbonate. But Daniel Piri. But the rest of his answers, they look legitimate, especially the sodium sulfide, where you put a 2 there. So those are the scenarios. Richard Monsa, you are overworking your work such that here calcium na bromine tatata mulembere ya chine yo. That's the thing, because calcium is 2 plus, bromine is minus. So since this one is 2 plus, you need 2 of the minus. 2 of the minus. So it should be CaBr2. Even this one, this is 2 plus, this is 3 minus. So the 3 goes there, the 2 goes there. So it's Mg3 and 2. Mupose kwa mano tata. Na pani sodium sulfide Na, if we equate plus, the 1 there goes down under the S, the 2 goes down under the Na. So it should be Na2S. So nga nika quiz akatata imobana nimo, nga mulile pofe kamo. Kamo fie, tata baba mwanza. So mupose kwa mano, I've explained how you do that nomenclature. Because for you, even the carbonate, it was differently written. Carbonate is CO3 2 minus. Why did you put the 3 outside there? I don't know. So try go practice some more. The same mistake of the oxygen for carbonate. Carbonate is C and capital letter O. Remember Lembea cobalt, Mr. Moffat. But the rest of your work is legit. Madam Tembo, you are the most accurate. Girl power. Girl power. This is very impressive. Kumalawi kulefuma knowledge yisuma sana. Abaneso aba kumalawi, wimuneso na Tembo wa kumalawi, ena Nadia Fionse, which is very impressive. Richard Monsa, same mistakes. Your C is correct. Your B is correct. Your A is correct. But your E is wrong. So you work out. I love the way you did your C. So Richard Monsa, meaning I'm sure you are catching up because your first attempt there was wrong, but then you have a better attempt on another thing. Doris, this is, was it nitrate? Doris, let me check. Was it nitrate? It's nitride, Madam Doris. A mistake, natural and instead you remember nitride. Nitride is just a small letter N, or a single N. Imumalemba nitrate. Because tulaiberesha basana mukano nitrate. So these mistakes, we make them a lot. Even there on sodium oxide. Remember the oxide is the one that has a 2 minus. The Na is that has a plus. So the 2 minus will go, the 2 will go punch by the 2, by the N. So it should be Na2O. So those are the scenarios. I think I've explained on pretty much a lot of things. I've been explained that we are making silly errors, especially with mixing like iron nitrate. It's a mistake that a lot of your friends make. Otherwise, nomenclature is very easy. In the next topic, we'll look. I'll just give you the table for the polyatomic anions, the nitrate, the nitrite, so that you know them. Then we'll look at those ones with variable oxidation states, the transitional elements, the transitional metals. So for them, you remember, so I want those of you who remember what you meant when you said copper 2 oxide and copper 1 oxide. Why? Because the 1 and the 2 were trying to explain the oxidation state, which to a lot of us is still referred to as the valency. I can give one person to conclude what they've learned because we're only remaining with 3 minutes. So anyone to conclude what they've learned or to ask an educated question in which if I'm using my last 30 seconds, I'll help all of you. Anyone? Jackson? Jackson Muntete?
Yes, sir.
Yes, you can say your thing, sir.
Yes, sir. Jackson here. Yes, sir. Jackson Mukete. Yes, sir. Things are very simple. Just to add on some knowledge on everything that has been said. When we have got a non-metal, for example, sodium and chlorine in the ionic bond, which makes sodium chloride. We know that sodium has got a charge of a plus, and then chlorine has got a charge of -1. So the only thing that these two elements are going to do is that the charge of the sodium is going to cross over to chlorine, and then the charge on chlorine is going to cross over to sodium. Why have they crossed over? Because they've got the same number. The other one is 1, and the other one is 1 as well. And so then there are instances where we've got. Yes, sir. There are instances where there's there are instances where there is an odd number on a non-metal and an even number. I'm talking about the charges. Yes. An even number on the metal.
Yes.
So the same thing happens again. There was that we used to call it. We like make a cross in between if you can recall.
And that cross is very acceptable even now. You should be able to cross the numerical numbers, okay?
Yes, sir. Because the problem is that these are new students who have come in as first years. The picture that we have towards college.
Okay, sir. Jackson, you are breaking heavy. And then I'm
very
remaining
but
with
it's
less
the
than a
same
minute.
stuff that we used to learn in grade 12. It's the same stuff.
Yes, it's the
sir.
same stuff.
Can you get me?
Okay.
It is the same. It is the same style. There's nothing that has changed.
Okay, sir.
So
he has
because of poor
explained.
network, I'll just end there.
Okay.
I'll just end there, sir, because of poor